When you were in grade 6, you learned basic relative motion. And by relative motion, we mean adding vectors together. If I said you were on a moving walkway at 5, the walkway was moving at 5 meters per second, and you were walking at 2 meters per second, you would have intuitively known that your velocity relative to the ground was either 7 or 3, right? We add those vectors together. The 5 meters per second plus 2 meters per second gives me 7, or 5 plus -2 gives me 3, depending upon the direction that I'm walking. Yesterday, we learned relative motion in 2 dimensions. We learned that we still have to add vectors together whenever we're doing a relative motion problem, but the way that we add the vectors together is different. The way that we add them together is by getting a right angle triangle, vector diagram, front to back, head to tail, and then resolving it, solving for usually the resultant vector, which we call the dotted line vector. We defined 2 types of vectors yesterday, the solids and the dotteds. The solid line vectors are sometimes what I call the contributing vectors, because they're the vectors that contribute to my actual motion. If I have a wind, that doesn't mean that I'm necessarily going to go in the direction of the wind or the speed of the wind, but it does mean that it's going to contribute to my motion. If there's a river current, it's the same thing. If I'm trying to swim across a river, straight across, but yet there's a river current that's downstream, then that's not going to make me go straight downstream, but it is going to contribute to my motion. It's going to change my motion from where it would otherwise be. Now, if I'm going across the river and aiming straight across, that also contributes to where I go. But because of the way that I aim and the river current, I end up going at a certain angle downstream. If I head in a certain direction in my airplane, then the wind and the way that I head are going to both contribute to the way that I actually go. The airspeed, which if you read the back of those in-flight magazines and you see the airspeed of all the different airplanes that they have listed in the back, yeah, that's the speed in still air. How fast in the absence of a wind can this airplane go? Sometimes we know we go faster, right? You're on an airplane sometimes and the pilot says, we're a little bit behind schedule, but there's a tailwind, so we think we can make up some time and arrive on time. A tailwind contributes to the motion of the airplane, as does how fast the airplane could travel without the wind. Those two combined give us the actual motion of the airplane. All of these things contribute to the actual motion, and hence we call them, or hence I make them solid line vectors. As opposed to these dotted line vectors, which really are our actual motion vectors, it's the solid line vectors that contribute to those dotted line vectors or the actual motion. So for instance, if a question says that I'm swimming across the river and I actually go directly west across the river, then that would be a dotted line vector. That's a resultant vector. That's a couple other vectors contributing to that one. If I want to go in a certain direction, let's assume that I'm smart enough that if I want to go in a certain direction, I actually go in that direction, or the pilot of an airplane wants to go directly north towards Edmonton. Let's assume that he or she actually goes north towards Edmonton. Okay, that would be a solid line vector, a resultant, a thing that comes as a result of wind speed, the way they aim, and so on and so on. Also, another solid line vector, another vector that is a resultant vector, or dotted line, I should say, is our ground velocity, the velocity of the boat, the ship, the person relative to the ground. Okay, so bottom line is this: if it contributes to the actual motion, it's a solid line vector. If it is the actual motion, it's going to be a dotted line vector. We did an example yesterday. I'm not going to go through this entire thing again, but I will just draw solids and dotteds just so we have a little bit of review of that and keep that straight. It says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. He heads or she heads directly north. Does that mean he or she actually goes north? Not necessarily. In the absence of a wind, maybe he or she does actually go directly north. But we don't know that for sure. But what we do know is that contributes to where the pilot goes. If the pilot is aiming north, then clearly that's going to play a factor in where the plane actually ends up going. So we're going to draw that as a solid line vector. We make that 200 kilometers per hour to the north. But there's a wind of 50 kilometers per hour to the east. That's a contributing vector as well, a solid line vector. 50 kilometers per hour wind doesn't mean I'm going to go to the east at 50 kilometers per hour, but it does mean that that's going to contribute to where I actually go and the speed that I actually go at. These are both solid line vectors. And then, of course, where the plane actually goes is our resultant vector. That's a dotted line vector. What do we got to be careful of when we're adding these together? What's our goal? What's our goal when we add these together? Always the same as it was when you wrote your quiz a minute ago with those funny angle questions. What's our goal? Get a right angle triangle, right? We can get a right angle triangle pretty easily here. We just connect these together and then draw a resultant. But how do I connect these together? Tell me where I'm going to label it. Position 1, 2, 3, or 4. How many people say position 1? It's not going to be position 1 because that leaves us with head-to-head. Okay, that doesn't work. How about position 2? Does that work? Yeah, that could work. Okay, that's not my preference. My preference would be position 3 because it's head to tail, but position 2 will work as well. Just means our angle is going to be 90 minus whatever we get. Position 4 doesn't work, right? Because that would be tail to tail. Got to be head to tail, just like we were with all those other vector diagrams that we've been around for the last few days. So let's label this as 50 kilometers per hour. And let's label this as our dotted line vector right here. We're going to call that R. We're going to call this theta drawn at the very start of the vector diagram. Make sense? Now we can do the Pythagorean theorem, which we did yesterday for this question, and the inverse tan function for this question, which we did yesterday. Right? We gave you a couple questions to work on yesterday on your worksheet. I want to take a look at maybe one of these questions to see how it's going here, okay? I didn't assign it as homework, but I think most people got through question number 1 at least. It says a pilot heads her plane with a velocity of 250 kilometers per hour to the north. There's a wind of 100 kilometers per hour blowing west. What's the velocity of the airplane relative to the ground? She heads in a certain direction. That would be what? Solid or dotted? Does that contribute to where she goes, or is that where she goes? You ever find yourself, how many people drive here? Okay, so do you ever find yourself driving in towards Calgary and there's one of those strong Chinook winds blowing across from the west? It's just crazy, crazy windy, and you're just fighting it the whole time to stay on the road. You ever notice sometimes your steering wheel is turned like this, like cranked way over there, so that you can go straight? Do you ever notice that? Some of you have. A few of you are nodding, I see. Okay. You're aiming somewhere over there, northwest. Why are you doing that? Well, because there's a strong wind blowing to the east. And you know that that vector and that vector combined give me this vector. Where I'm aiming way over there isn't where I go. I'm aiming way the heck off the road. But I have to aim off the road to compensate for the wind that's going this way. So when I aim in a certain direction, that's not my motion. When I aim in a certain direction, that along with the wind contributes to my motion. So if we're heading a plane directly north, we're going to make that a solid line vector that contributes to our actual motion, 250 kilometers per hour. Now we got another vector, that's the wind that's blowing to the west, and that's only going to be 100 kilometers per hour. That's a solid line vector as well, just like that Chinook wind blowing to the east that's in combination with the way that I steer is causing me to go straight ahead. This wind is blowing me to the west that is in combination with the way that I aim, causing me to go at this angle up here. We're going to label this as R, we're going to label this as theta, and then we're going to solve for R by doing the Pythagorean theorem. Let's say 100 squared plus 250 squared equals whatever, square root that, and we end up getting an R value of 269, or around that to 3 digits, yeah, it would be 269 kilometers per hour. And theta is going to be the inverse tan function of opposite over adjacent. What's the opposite side here, 250 or 100? Quick, just tell me. What? It's going to be 250, is that right? Is that opposite? The opposite side is the one that does not touch the angle. The 250 is right beside that angle, so that's going to actually be adjacent. The 100 is the opposite side because it's the only one of the three sides that's not touching the angle. We're going to say it's the inverse tan of 100, which is the opposite side, divided by the adjacent side, and that's what we end up getting there. Let's pull out the calculator again. Let's say the inverse tan of 100 divided by 250 gives me 21.8 degrees. How do we express that? 21.8 degrees what of what? Yep. This would be west of north, right? In order to get to that spot, in order to get right from here, right to here, we have to go north and then we have to go west. We went west after we went north, so we'll call it west of north. Now, if you had have drawn it the other way, like this, then you would have gotten the same value of 269, but you would have got an angle of 68.2 degrees north of west. How many people, when they were doing that, got 21.8? Okay, how many people, when they're doing that, got 68.2? Okay, which one's more correct? They're both correct, right? They're both 100% correct. All right, I'm going to give you a couple more minutes to work on questions 2 and 3 here before we move on. Just a word of caution that I mentioned to you yesterday. There is a typo in question number 2. It says the airspeed of an airplane headed north is 40 meters per second. This should have been a wind of 15 kilometers per hour. Now, if you've already done this, don't go back and redo it. Okay, just keep the 15 kilometers per second. But understand that that's like an unrealistic speed of a wind, right? 15 kilometers per hour makes much more sense. If you're doing it in kilometers per hour, right, meters per second, kilometers per hour, doesn't really matter which unit you use. But what am I about to say? It doesn't matter whether you use kilometers per hour or meters per second in these questions. But what's the but? You got to be consistent at least, right? If you're using meters per second, that's fine. Stick with it all through the question for every piece of data. If you're using kilometers per hour, that's fine, but you got to be consistent through the question. So if you haven't done this already, then understand that this is 15 kilometers per hour, not per second. Make sure you either convert this to kilometers per hour or this to meters per second and go from there. All right, I'll give you a few more minutes to work on 1 to 3 here. All right, time to take a look at number 3. It says, I should press record. I am. There we go. Number 3 says, we got a boat whose speed in still water. This is like the airspeed of an airplane, right? This is how fast the airplane or the boat can go in the absence of a river current. This isn't the actual motion of the boat unless there's no current. Okay, this is something that contributes to the motion of the boat. So we're going to make this a solid line vector. There's a river current that's flowing at 1.2 meters per second to the south. Okay, we're going to also make that a solid line vector because that's contributing to the motion of the boat. That's not where the boat goes. The boat doesn't go south. That's just contributing to the motion of the boat. Now, we want to find the velocity of the boat relative to the shore. In other words, we want to find a dotted line vector, the resultant vector. Okay, the motion that results from the current and the speed of the boat in still water. Well, what if the boat is headed south? Technically, we've got a boat heading south at 2.5, and we've got a river current going south at 1.2. We don't even need to draw the vector diagram there, right? We've got it drawn, head to tail. That's correct, but we don't need to draw that because if you want to add those together, it's just follow the grade 6 rules of vector addition. Negative 2.5 plus negative 1.2 gives me negative 3.7 meters per second. Or you could have said what? 3.7 meters per second to the south would have been fine as well. Good. What if the boat is headed north? Well, we could draw a vector diagram, although we don't really need to. We got 2.5 meters per second, and then we got another one that is 1.2 meters per second to the south. We add those together. 2.5 plus negative 1.2 gives me a positive 1.3 meters per second, or 1.3 meters per second to the north. Again, straightforward, right? The grade 6 rules of vector addition because everything's one-dimensional. But what if the boat is headed west? We're aiming to the west at 2.5 meters per second. But there is a river current to the south at 1.2. Still drawn head to tail like the diagrams in A and B were, but this time it's a two-dimensional problem. two solid line vectors come together to cause a resultant vector. They come together to cause the actual motion of this boat. So we find the actual motion of this boat, we call it r, and theta by doing the Pythagorean theorem and by doing the inverse tan function. Tell me, in this picture, in this diagram right here, which is the opposite side? Is it 2.5 or 1.2? 1.2 is the opposite side because it's the one that's not touching the angle. Okay, this is the resultant, the hypotenuse. This is the adjacent side because it's the other one that touches the angle. So we're going to say the opposite side is the 1.2, the one that's not touching the angle. Adjacent is 2.5. Okay, so let's get this now. We're going to say r is equal to the square root of 1.2 squared plus 2.5 squared. We get a value of 2.77, or we get 2.8 meters per second. So this boat, in the absence of current, can go at 2.5 meters per second, but with the current, it ends up going at 2.8 meters per second. So it's sped along by the current here, helped along. Now let's find the angle at which it actually goes. I'll say the inverse tan function of 1.2 divided by 2.5 bracket gives us 25.6 degrees, or 26 degrees south of west. So as a result of the speed that I can travel with no wind or no current, and a result of the current, my actual motion is 2.8 meters per second at 26 degrees south of west. All right, I'm going to give you a few minutes to work on questions 4 and 5 as well, and I know some of you already have. Let's get you to continue there, but I'm going to give you a little hint for question number 5 before you get too deep into it. 5A is a straightforward question, just like the other questions that we've done. But what you got to be careful of here in 5A is that when you draw a vector diagram, you draw it with one type of quantity or another. You can see in this question, we've got a velocity, 25 meters per second, a velocity, 8 meters per second, and a displacement of 850 meters. In your vector diagram, don't do both. Make it either velocity or displacement. You got it? Just like you can't use kilometers per hour or meters per second in the same diagram, you can't use velocity or you can't use displacement in the same problem. So use one or the other. I'm not going to tell you which one yet. And finally, in question B and C, I saw a couple of you already working on this. When you're doing this, when people were doing this, I saw them using V is equal to delta D over delta T. That's good. Okay, that's a good insight. But I'm going to give you one little hint here, one little word of caution, and that is this. When you're solving this for time or see how far downstream it goes, be careful which velocity you use. Be careful which velocity you use. Okay, be conscious of which velocity you use. Don't just pick a random velocity quickly. Think about which velocity you should use for question B and C. All right, the last example that I want to do with you today is up on the board here for you right now. This one says the pilot of an airplane wants to go directly north. Wait a second, the pilot wants to go directly north. Well, let's hope that this pilot is competent, and when he or she wants to go directly north, he or she will actually go north. We're going to call that the actual motion of the airplane to the north. Is that solid or dotted line vector? If he or she wants to go north, or he or she actually goes north, we're going to make that a dotted line, aren't we? That's a resultant vector. But here's the thing. In any other problem that we've done, we've had to find the dotted line vector of the resultant. This time we have it. So be careful. Let's draw my dotted line vector as 500 kilometers per hour to the north. Now I've got another vector here as well. It's a wind that's blowing to the east that contributes to my dotted line vector. So that's going to be a solid line vector. We're going to draw that to the east at 85 kilometers per hour like this. Now, where am I going to draw it? Where do you want to draw it on this diagram so that we have our normal rules of vector addition or normal rules of vector diagrams correct? We got a solid line vector and we got a dotted line vector, dotted meaning the resultant vector. Where should I draw this? Position 1, 2, 3, or 4. I'll give you a hint. There's two answers, two correct answers to this, and two incorrect answers to this. So basically, you got a 50% chance of getting this correct. Who says position 1? Position 2? Position 3? Position 4? All right. It's unanimous. 1, 2, 3, and 4. Listen, we're not going to draw this right here. I know some of you are thinking, well, that's head to tail. Isn't that what we want? No, the resultant vector, the dotted line vector, needs to go from start to finish. So if I have my resultant vector drawn first, why don't we draw this wind vector like this so that the resultant vector goes to the finish, goes to the end. Let's label that as 85 kilometers per hour. And let's draw my other vector right here as the vector that I need to aim at. My other solid line vector, the one that contributes to my resultant vector. Now, look at what we've got up here. Still got a right angle triangle, right? That's good, because that's what I want. I still want to find the hypotenuse, but the hypotenuse is not the resultant. The resultant is already given to me as 500 to the north. It's not the longest vector this time. The longest vector is where I aim. So I'm going to aim at a certain speed. That, combined with the 85 kilometer per hour wind, is going to result in my actual motion, which is to the north. So I want to find the hypotenuse. Mathematically, it's no different than the other questions I've done. It's just conceptually a little bit different because the one that I'm solving for, not the resultant vector, is the hypotenuse. We're going to say v, the speed that I aim at, is equal to 85 squared plus 500 squared. And we're going to say theta, down here, always drawn at the start, theta is the angle that I have to aim at, which is the inverse tan of opposite 85 over adjacent, which is 500. Let's figure this out, both of these. 85 squared plus 500 squared gives me 507, or 5.1 times 10 to the 2 kilometers per hour. And theta ends up being the inverse tan function of 85 divided by 500, which gives me a value of 9.6 degrees. This would be 9.6 degrees east of north. So let's think about this. Okay, logically for a second, physics aside, vectors aside, just intuition. If I want to go north, but there's a wind to the east, where do I got to aim? Okay, I want to go north, but something's blowing me that way to the east. I got to go somewhere northwest-ish, right? Somewhere to the north and somewhere to the west, which is exactly what we found there. All right? Solid line vectors versus dotted line vectors. Keep that straight, okay? If you draw, why is that a big deal in this question? If you draw that first vector as a solid line vector, draw that as 500. Look what happens when you draw the 85. Look what happens when we draw the 85. Oh, now we're going to draw that there because it's got to be head to tail. That doesn't seem like a big deal because the value of our hypotenuse will still be the same. The problem is our direction will be wrong, right? We're not going to get 9.6 degrees east of north. We'd get west. Sorry, this should be west of north. West of north, right? We would have gotten east of north. So it's important. It's important that you draw this correct so that you get the correct direction there. Hey, some of you would have got this. Some of you would have got east of north and written that down as an answer, but yet it doesn't make sense because if I want to go north and there's a wind to the east, I'm not going to aim to the east. I'm going to aim to the west, right? If you're swimming across a river, you don't aim downstream so that you can go straight across. You aim upstream a little bit so that you can end up going straight across. Okay, your homework tonight is that worksheet up to question number 6 if you haven't finished up to number 6 already.